Hello students, so in the last video I have shown you how to solve question number 5 from exercise 1C. I showed you how to solve from 5 sub number 1 and 3, and I asked you to do question number 2 by yourself. In case you have any doubt, or if you have got wrong answer and unable to clear doubts, so here is the solution to question number 5 2. Please see, let us do this. So the question remains same. The question was, find the HCF and LCM of these two given positive integers, and after finding the HCF and LCM you have to verify that the product of LCM and HCF of these two numbers is equal to the product of these two numbers. Okay, these two numbers you have to verify, you have to check. So let's begin. So first I begin with 21. Okay, we have to find the prime factoration of 21. So as you know that when you start doing prime factoration of any given number, you should start with the first prime number 2. Now tell me, can you divide this 21 by 2? Can you divide this given number 21 by 2? The answer is no, because 21 is an odd number because of this unit digit 1. Okay, as you know that for an odd number we need 13579. 13579. Therefore, for odd number the unit digits the unit digits are 13579. Since it's 1, so obviously it's odd number. So odd number we cannot divide by 2. And since you cannot divide 2, so now the next number you should try is what? To divide is what? By the prime number 3. And 21. If you remember table of 3, then you'll know that 21 is a multiple of 3. So 3 sevens are 21. Okay. And we have got 7 here, and you all know that 7 is a prime number. The moment prime number comes, do not waste time, because prime number is divisible by itself only. So this 7 prime number we divide by itself. So 7 ones are 7. Okay, 7 ones are 7. So that means we have got the prime factors of 21, that's 3 and 7. Okay, now let us do the prime factoration of 315. Same here. In this 315 also, if you look very carefully, 5, the unit digit is 5, and 5 is an odd number. 13579. When you have unit digits, these numbers, no, 12357 13579, and is an odd number. That means 315 is an odd number, and odd number we cannot divide by 2. That's why we should try now to divide by 3. And for 3, remember, for big numbers, what's the test of divisibility? When you want to divide any given number by 3, the rule is that you add all the digits, and the total and the sum should be a multiple of 3 in order to be divisible by the prime number 3. Okay, so let's add all this. 3 plus 1 4, and 4 plus 5 9. And if you think of the table of 9, so table of 3, see the sum is here is 9, and you know 9 is a multiple of 3. 3 3s are 9. That means 9 comes in the table of 3. 9 is a multiple of 3, and the sum is also 9. So that means yes, we can divide this by 3. Okay, so let's divide 315 by 3. First we'll take only single digit, because 3 is same. 3 ones are 3. 3 ones are 3, and 3 here, 3 minus 3 is 0. That means no carry, no carry. Now whose turn? It's only 5, because of one number one time. Many students, what they do, normally, like many students by mistake, what they do, they directly do 3 5s are 15, which is completely wrong. Okay, so I want you not to repeat those mistakes, because here there's no carry with 1, so it's only one number you should divide one time. Okay, when dividing this way. So 3 ones are 3, remainder 0. Since only one's turn, but you know that 1 is smaller than 3, I cannot take 5 at the same time, because 5 will come in the later stage. So since it's only 1, so 3 ones are 3 big, because see, 3 is bigger than 1. So I should always take either equal or less. So that's why I'll not do 1 time. 3 1 times 3 big. So I'll take less than 1 time. This is 0 times. 3 0 times 3 zeros are 0. Now it's smaller. 3 zeros are 0. And 1 minus 0. Now see, 1 minus that 0 will be 1. Remainder 1. And that 1 will go and join it 5. That becomes 1 and 5, 15. So 3 5s are 15. Okay, 3 5s are 15. So here I can show you, look, If I divide in the rough also, 315 divide by 3. If you don't have confidence to divide like this directly, then you can always divide in the rough and get the answer. Okay, 3 ones are 3. It's only once turn, so 3 zeros are 0. Then 5's turn, remainder 1. Then 3 5's are 15, remainder 0. Okay, so that's why it's 105. Okay, now let's continue again. Since the last factor was 3, so let us again try by 3. Again for 3, since it's a big number, let us do the test again. 1 plus 0, 1. 1 plus 5, 6. 6 is the total, and 6 comes in the table of 3. 3 ones are 3, 3 2s are 6. Total is also 6, and 3 2s are 6. That means, yes, we can divide this by 3, okay? So if I take only 1 is smaller, so we should take two numbers, so this is 10. So table of 3, 3 1s are 3, 3 2s are 6, 3 3s are 9. 3 3s are 9 because it's 10. 3 3s are 9. 10 minus 9, 1. 1 goes and join with 5 from the left. It's 1 and 5, 15. 3 5s are 15. So now it's 35. Now let's see again we can divide by 3 or not, because the last divisors we have taken 3. So let's try by 3. Again for 3 we'll do same test. Let us add 3 plus 5, 8. Now think, does 8 come in the table of 3? 3 1 is 3, 3 2 is 6, 3 is 9. 3 4 is 12, 3 is 15, so 8 is not coming. That's why 35 is not divisible by 3. Okay, we cannot divide 35 by prime number 3. So 3 is not a prime factor of 35. So since 3 is not prime factor, 2 is not prime factor because of this odd number still. Then comes whose turn? We should now try to divide by 5. And yes, 35 we can divide by 5 because the unit digit is 5 here. We can divide by 5 when the unit is either 0 or 5. And since it's 5 here, we can divide. And moreover, 35 is a small number. You can quickly recall your 35 comes in the table of 5. 5 7s are 35. And here coming 7. And we all know that 7 is a prime number. So you can 7 itself is a prime number. So prime number we divide by, it's the 7 is a 7. Okay, so we got the prime factorization. So prime factorization of 21 is equal to what? 3 into 7, but we write in power notation. So 3 is only one time, so power 1, and 7 is also only one time, so power 1. Okay, and now we'll write prime factorization of 315. So we got what? 3 into 3 into 5 into 7. So we write in power notation first. See, if 3 is coming 2 times, 3 into 3. That means what? 3 is a prime factor, but we'll not repeat it. We'll just count how many times and we'll make it power, okay? So you can find the 3 into 3, I can write 3 square because 3 is coming 2 times. 5 I can write power 1 because 5 is only one time. And 7 is also power 1 because 7 is coming only one time in this prime factorization, okay? So we're ready with the prime factorization, okay, of these two given positive integers. Now we'll find HCF and LCM. First we'll find HCF. Therefore HCF of 21 and 315. Let me quickly tell you once again what is HCF. HCF means highest common factor, and when you do prime factorization you find the HCF numbers in this way. And remember the definition. HCF is something but is the product of only the common prime factor, only the common prime factor with the lowest power. Only common prime factor with the lowest power. So let's see which are the common prime factors here. You can see that in the prime fraction of 21 and in the prime fraction of 315, 3 is a common prime factor. 3 is a common prime factor. So right here, 3. And same way, 7 is also a common prime factor, because 3 and 3 are present in both the prime factorization of 21 and 315, and 7 are also present, okay? So 7. But with the smaller power, look. In 21, the prime fraction of, in the prime fraction 21, 3 has power 1. In the prime fraction 15, 3 has power 2. So which is smaller? Here also 3 and here also 3. Both are prime factors, okay? 3 and 3, common prime factors. But if you look at the powers 1 and 2, which is smaller? 1. So that's why we'll take power 1 with the smaller power, okay? For HCF, we should always take the smaller power or smallest power. And same here, see, in this prime factor 7 has power 1, in this in the other prime factor we have 7 power 1. Which is smaller or which is smallest? Obviously less than 1 is not there, so means 1 is smallest, so we'll take 1. Okay, clear? So 1 is the smallest power of both 7. Okay, so that means we have got, see, for HCF we have taken only the common prime factor. Look, I have not taken 5 because 5 is not common. 5 is present only in 315, but 5 is not present in prime factoration of 21. So 5 is not common, so I'm not writing. We had only common 3, 3 and 7 is uncommon with the smaller power. 1 is smaller than, no, 1 is the smaller power in 3 and 1 is the smaller power in 7. Okay, so they're equal, so we'll write 1. So now 3 is to power means 3 only one time, 7 is to power means 7 only one time. Okay, and now multiply 3 into 7, 21. Okay, yes, we have got the prime. So yes, we have got the HCF of this 21 and 35. Okay, so the HCF of these two numbers is 21, highest common factor. Okay, now we'll find LCM. Therefore LCM of 21 and 315. Now let me again tell you once again, LCM means lowest common multiple, and it is defined as the product of all the prime factor. All the prime factors are defined here, whether common, uncommon, doesn't matter. Okay, it should be all the prime factors which you find in both these numbers, all the given numbers. Okay, all the prime factor with the highest power. And keep in mind that after writing the prime factor, all prime factor, we should write the power notations of those prime factor with the highest power. Okay, so let's first write all the prime factor, all the prime numbers. See, 3 is a prime number, prime factor, 5 is a prime number, and 7 is a prime factor. Means what? 3, 5 and 7, 3, 5, 7, these are prime numbers. See, 3, 5, 7 are present, 3, 5, 7, these are prime numbers. So yes, 3, 5, 7 I've written. Now we write all this with the highest power. If you look at the power of 3's, so 1 and 2, the 2 is the highest, 2 is the bigger power, higher power, so this is the highest power, 3 square. 5 has only 1 power because there's the highest here only, and 7 is 1, 1, there's only 1. Okay, the 1 is the highest power. So now finish power notation. Now we'll multiply. So first remove this power from here and write in normal form, standard form. So 3 square, 3 square means 3 into 3, not 3 into 2. Okay, 3 into 3, 9. 5 power 1 means 5 one time, 7 power means 7 one time. Okay, and now let us multiply. Okay, 9 into 7, okay, 9 into 5, 45, and 45 into 7, 75, 35, 28, 29, 30, 31. So it's coming 315. That means the LCM of these two given numbers is 315. Okay, it's a really peculiar question because the given numbers are also 21 and 15. HCF has come 21 and the LCM has come 315. Okay, but doesn't matter, these are some peculiar questions, so peculiar numbers, so just take it them as normal, take these things as normal. So the first part of the question is finished, find the HCF and LCM. Okay, now the second part is what? Verification. Okay, verify that LCM into HCF is equal to product of two numbers. So here we do now the verification part. So let's do now the verification. So for verification, we copy the given statement, and the given statement here is what? Look very carefully in question 5, and verify that LCM into HCF, that is LCM into HCF should be equal to what? Should be equal to the product of the two numbers. The product of the two given numbers should be equal to product of the two numbers, means two given numbers. So we've written the statement. Now we'll just verify. To verify, we give here this implies or this means. Now we'll put the values. Just to verify, you have to show that these two are equal or these two are same for a particular question of any question. So let's put the value. So LCM, what you got? LCM, say students, LCM you got 315. So put the value of LCM 315 here. HCF, what you got? HCF, HCF of this two given numbers we got 21. Put here 21. And see the product of the two given numbers, and see which are the two given numbers here in this question number 5 2. The two given numbers are 21 and 315. So right here 21 into 315. Okay, these are the given numbers. So let us multiply them to get the answer. So now we multiply 315 into 21. Okay, 1 into 5 5, 1 into 3 1, 1 into 1 1 into 3, 25 10, 2 2 into 2 2 plus 1 3 2 3 6. So it's 6,615. So it's 6,615. And yes, students, if I multiply this 21 and 315, 21 and 15 already multiplied. And moreover, you know, in arithmetic, for any given integers, a into b is always equal to b into a. This is called commutative property. So means what? 21 into 15 will give us same answer as 315 into 21. Okay, since the numbers are same, so the product also will be same. So it will also give us 6,615. Okay, the numbers being same, obviously this two product and this two product will be equal. So means we have proved that. So therefore we got what? We got that left hand side is equal to right hand side. Left hand side means the product of LCM, and right hand side means the product of numbers. And yes, they are same, they are equal. So we have verified. So hence verified. Okay, so this completes your answer for question number 5-2. Okay, so given numbers here, we have done the prime factorization, we have found the LCM, and we have done the verification. Thank you.